This is the event they put on every year to tell the press and analysts about their next generation of hardware for the mobile smartphone space. We're talking new Cortex A cores, new GPU, and a new SoC design for their clients. Now, why is this important? Well, before you click off, generative AI is a thing, and yes, as much as I hate the name, and I hope you hate it too, it's important to understand how much compute goes into these platforms and the roadmaps that they're putting forward. In this video, I'm going to go through their new architecture designs, their new cores, and see where they're going to go next. But first, a word from our sponsor.
If you're interested in some good merch, then head to merch.techtechpotato.com.
So yeah, if you're like me, generative AI, just as a phrase, is a little bit grating. As I'm recording this, it's been about 2 weeks since we first started talking about generative AI. What does that mean? That means you have an AI model and you're creating a fuzzy output that has no defined endpoint kind of reward function. Usually we think of AI as in you put something in and you get an answer out. Generative AI is like Stable Diffusion. You put some inputs in and you get an output which may be aesthetically pleasing or not. The beauty is in the eye of the beholder. The same with these large language models like ChatGPT. Now, the question is, how much compute can we put into a platform such that we can run some of these models at the edge on our devices without needing the massive power consumption of compute? This is why companies like Arm are developing IP which pushes the boundary in performance per watt forward. This not only means new AI-specific instructions, but also getting to the point where the performance per watt, the performance per instruction, is beneficial, that even though these models are growing in size, they actually become applicable to run on these devices. Now, Arm doesn't have any particular sort of NPU IP that they're talking about today, mostly focused on CPU, GPU, and SoC platform level optimizations. However, as we move into things like gaming, where AI is becoming more prevalent, and where you have dedicated ISPs and other compute layered on top, the idea is that Arm is providing the backbone to those designs for which a chip designer's NPU or dedicated IO compute is put onto it. So for example, Qualcomm, they take Arm Cortex cores, X cores, A cores, and then they layer on their Hexagon NPU. Same with MediaTek, Cortex X, Cortex A, and then their own NPU. Apple designs their own ARM-based cores, but then also has an NPU. And this is the point that Arm is trying to make during my time here, that they aren't necessarily doing the AI IP themselves, but they're providing the backbone to feed that IP, which requires high performance cores, architectures that support high performance, and the ability to build an SoC with the right profiling tools, such that when you do apply it to things like the camera app or to games, that you have the ability to optimize your performance level for the form factor and the use case. So let's start at the top, Cortex X. Now, if you're not familiar with Arm's naming scheme, the X family of Cortex cores, Cortex X, I get it. But X is basically their high-end performance single-thread leader. This is the highest in IPC, and it targets the highest frequency in all the partners that use the Cortex X cores. Seeing Qualcomm use Cortex X all the way through its latest Snapdragons, MediaTek in its Dimensity 9000 series also using X in their latest products. And in terms of performance and performance per watt, it's pushing there up against the best designs in the market. Now, X4 is the next generation, building on the X3 that are currently in devices today. And then, as you can imagine, there are performance uplifts across the board, standard microarchitectural enhancements. I'll put a slide up so you can see some of them in more detail. But one of the big things here that Arm does with its IP is that it has a configurable cache sizes. So when you're looking at L1 and L2 on a per core basis, if you're a Qualcomm, if you're a MediaTek, if you're anyone else, then or a Samsung, you can essentially go to Arm and say, I want this core with 512 kilobytes or 1 megabytes of L2 cache. This generation, Arm is allowing 2 megabytes of L2 cache, which essentially helps push the performance window of the X core from smartphone into a more applicable mobile format. So think notebooks, though that isn't necessarily what they were talking about today. In the mid-range, you have the Cortex A720 cores. Now, 720 is building on 715. We're seeing a 22% in performance efficiency between the two. And this is the mid-range workhorse. You use the X for responsiveness. You use the X for when you immediately hit the screen and you want an app to pop up really quickly. But when you've got a really strong workload, it's having 3, 4, or 5 of these A720 cores that are really going to push performance through. And again, additional enhancements, I'll put up a slide, and I might even do a separate video on each of these cores to go through the microarchitecture. But we're going to see custom designs with these cores, leveraging new compute. They've even got reduced precision format to actually help with machine learning compute. And the thing about the 720, this new 720, is that it will come in 2 flavors, either performance optimized or area optimized. So if you think about when you design a core, you've got your prefetchers, you've got your caches, you've got your buffers, you've got your execution units, and how you lay it out in your floor plan when you send it to the fab matters in terms of what your peak frequency is going to be, what your area efficiency is going to be, and what your power consumption is going to be. ARM is going to be offering 2 variants of the A720. They're going to offer a performance optimized, so this is the largest area design, but the best performance per watt and the highest frequency. Or if a customer is looking for a smaller die size, they may go for the area optimized version. You do lose a little bit in frequency, you do lose a little bit in performance per watt, but you do save the money in the design of how many chips you can make per wafer. ARM told me here that realistically, they're trying to push as many clients to the performance optimized version because it's easier to manufacture. There's fewer constraints on some of the clock gating and things like that might reduce yield. However, both of these are going to be proved in silicon over time. We may see that the mobile markets may take the performance optimized version, but we may see some embedded markets take the area optimized version where peak performance isn't necessarily a major concern. They kind of already do this with the X cores, and my feedback to ARM is it's going to be a little bit confusing, especially in the smartphone space, if we get SoC manufacturers, some of which are using the performance optimized and some of which are using the area optimized. We can obviously check for performance, but it's hard to check the area differences without taking the chip out, grinding it down, doing imaging like that. So my feedback was more, you really should have 2 different names for these cores, and they took the feedback honestly as take it into consideration. It may not matter at the end of the day because the performance difference may not be that much. We'll actually have to test it to see. Though it's going to be interesting to see if we can actually get hold of both versions of these cores to do the test. So then the newest efficiency core is the A520. Again, an update over the A510. And the A520 actually brings the family together. So all these 3 new cores are ARM v9.2. So along v9.2, update to the ISA, you get security enhancements, you get different tweaking of different elements of everything. However, the big headline here is that all these cores will only support 64-bit, no 32-bit operation. And that's actually kind of important. We've had this push from 32-bit to 64-bit for a long while now. There was even back in the day a Qualcomm executive that said nobody needs 64-bit, and then suddenly everybody needed 64-bit in mobile. But we're getting to a point now where ARM is developing cores with no 32-bit in mind. The reason why they've had to hang on to 32-bit for so long, with the A710, for example, is because there are ecosystems in the world today that still rely on 32-bit. Now, if you've got a smartphone, it's going to be 64-bit at this point. When you go to your app store and you download an app, the app store will say, do you want the 64-bit version or the 32-bit version? Or it'll ask the smartphone that you're holding. And if it detects 64-bit operation, it'll send you the 64-bit version of the app. If you only have a 32-bit device, it'll only send you the 32-bit version of that app. Moving to a 64-bit only mode means that all the apps you have to use have to be 64-bit. And what ARM's been doing with not only with the Google Play Store, but particularly in China, where there are multiple download stores for each of the major vendors, for Oppo, Xiaomi, and what have you, the big issue there was trying to get all those developers who are developing for those app stores to build 64-bit versions. There were still some developers building only 32-bit versions. I think they showed a graph, and I'll show it on screen, where or at least 3 years ago, only 70% of the apps on these marketplaces actually had 64-bit versions, and it's now more like 98%. We just seen the first 64-bit only CPU using ARM Cortex cores, the Dimensity 9200, which was launched earlier this year. That's the first 64-bit only chip, and then the Pixel 7 is the first 64-bit OS only. So there isn't even a 32-bit OS mode for any of those apps to run in. Essentially, they're eliminating and removing the dead weight of 32-bit going forward with these future ARM v9.2 core designs. And that has to propagate in the market. And they finally feel that this is the right time to do that now. So alongside the 3 new cores is the DSU. So this is the Dynamic Shared Unit. We've all heard of Big Little. This was ARM's name for its heterogeneous core design. You have big cores and little cores. Now, most of the high-end smartphones, the flagships and the premiums, have big, medium, little. And that came about through the feature in ARM v8 called Dynamic. That's D-Y-N-A-M-I-Q, Dynamic. And the Dynamic Shared Unit is the thing that brings it together. With Big Little, you were limited to quad-core clusters, and you could have 2 of them. You may have been able to have more. I can't remember exactly because it's been so long now. With Dynamic, the idea is that you can have up to 8 or 7 to 8 core clusters, and those could be as many cores per cluster as you need, maybe up to 8 or so. So what we're seeing is in a modern 1 plus 3 plus 4 is that you have 3 clusters, a 1-core cluster, a 3-core cluster, and a 4-core cluster, all essentially combined within this DSU, the Dynamic Shared Unit. And the Dynamic Shared Unit has a cache. In this generation of cores, the maximum cache you can actually have for that unit is 32 megabytes. If we compare it to other computer architectures, this is essentially the L3. And ARM had a previous limit of either 8 or 16 megabytes for this DSU. What the 32 megabyte option does is provides a way for laptops to have large amounts of L3 cache for their workloads. So each core individually has a private L1. The X and the A700 series has a private L2. The A500 series has a shared L2, kind of like an Atom. And then on top of that, you have the fully shared L3 in the Dynamic Shared Unit. Some SoC vendors also put in a system level cache behind that, 4 or 8 megabytes. Not entirely obvious why sometimes, maybe because of an ISP or a dedicated signal processing block. But that DSU then enables the core complexes to interface with the rest of the chip through the communication fabric. The DSU is also where we see all the security, lots of enhancements of security this generation. Again, I'll put up a list so you can see, and maybe we'll go into them into more detail in a different video. But this is generation on generation improvement, DSU 110, now DSU 120. One of the features here, or 2 of the features that I think I should highlight is the L3 cache within the DSU. So like I say, up to 32 megabytes at 8 banks. So you can have 8 banks of 4 megabytes each. But there are features where the system can turn banks of L3 off if you're not using them to save power. They can turn the banks half off to save power, or they can put them in a low power mode. Again, also to save power. And you have different your performance changes depending on which mode you put it in. But for the power saving, and there's a slight penalty to go back to full performance mode. And depending on which mode you're in, a core being active might wake it up. But the idea is that you have various levels of being able to turn your L3 cache off without having to lose the data. And that's a key component of, again, waking the smartphone up, pressing the power button and having everything available at your fingertips. So that's really important. Another thing with the DSU is cache stashing, which is almost essentially a direct memory access. What do I mean by this? So how a vendor like Qualcomm, like MediaTek, will implement their NPU, their AI engine, into these chips is an interface through the Axi bus. And the whole point is maybe you want to take some memory from an accelerator on die and then push it directly into the L2 or the L3 cache of a core. With cache stashing, you can do that now. Theoretically, you could do it 3 generations ago, but for some reason ARM took it out with the DSU 110 and it's back in with the DSU 120. It's a lot more applicable now with AI and with GPUs as well. And on the GPU front, ARM is introducing their next generation GPU. And this is actually a completely different, they're calling it a new family of GPUs. So we've just had 4 generations of their Valhalla architecture, which last generation they went from Mali to Mali and Immortalis, Immortalis being the performance optimized high core count versions. Remember what I was saying with the A700 series, the performance optimized versus the area optimized. Mali tends to be more area optimized, whereas Immortalis is 100% performance optimized. With this new generation, the 5th gen, technically called Titan, but the official marketing name is going to be 5th gen. And with the new cores, you again will have that Immortalis version, which is 10 cores plus. It goes up to 16 cores at the full fat solution. And then you have Mali G720, Mali G620 for the lower, mid-range and lower segments of the market. If you have an Immortalis, you're dedicated to a ray tracing unit. For the Malis, it's optional. Ray tracing unit is interesting here because now it's power gated. If you're not ray tracing, it will power down the ray tracing unit, so it's drawing 0 power. If you need ray tracing, it will turn it on, and it will balance the power as is needed. Again, performance uplifts this generation with the GPU. The big one here is deferred vertex shading, rather than deferred vertex rendering even. Rather than the forward rendering method that we've been used in GPUs, since almost day one, this method of rendering actually saves a lot of memory bandwidth, up to 40% in some cases. We've always said that gaming tends to be a memory-bound workload. How fast can you feed the GPU, feed the beast? Using this method of DFS, ARM is now quoting on big titles in the market that it can save 40% DRAM bandwidth. Now, with that saving, you could either save power, game for longer, or push the frame rate and game at a higher performance level. So it's giving the game developers more opportunity to optimize for a given power performance window. There are other optimizations in there. Again, I'll put up a list and maybe do a more dedicated video on the more details of the GPU. But if we combine the CPU, the GPU, and the DSU all together, you have what is called an ARM total complete solution, or total compute solution, sorry, TCS23. So this is essentially their 2023 reference SoC IP design. Last year was the 22 version, then we had a 21 version. We've also got a roadmap out to the 24 version. I'll show this slide. But it basically means that every year on year, they provide this TCS, this total compute solution, to partners in advance, basically saying, we believe that this is a common representation of a smartphone SoC. You obviously need a few more things to actually get it to complete. But this is actually what they simulate in FPGAs to help their customers and their clients optimize their own endpoint SoC in terms of performance, accuracy, die area, everything like that. So if a customer wants to get involved in a platform, ARM will send them a TCS, a total compute solution, and it will come with these cores enabled. It will come with the X, the A720, the A520, the Immortalis GPU, the new DSU, and all the extra improvements that they made to the platform. Also make improvements in software. Again, that's a whole other conversation. And what being here with ARM and speaking to them is that they're seeing good traction with these kind of TCS reference designs with their partners, because it helps provide their partners a base, on which to compare previous generation hardware with, but also if they have their own custom, again, GPU or NPU or everything else, they can also add it into the simulation matrix and find where the performance on the spectrum lies with the next generation cores. Then they can decide what they want to actually build in silicon, tape out, put into product, and sell to partners. So what ARM's doing here is looking end to end from the mobile space. If there were any criticisms from this announcement, is that there's not necessarily been much talk about, say, laptops, and that's not to say ARM's not looking at laptops. It's very much ARM wants to be in compute solutions that are important to the market, and laptop is one of them. There's just nothing specific about laptop today. I will say that the DSU actually allows for 14 core designs this generation. Is it 12 or 14? Yeah, 14, because the example they showed is 10 X4 cores and 4 A720 cores for a what would be considered a reference high-powered platform for laptops. And what we're seeing in laptops today is arguably 3 generations old ARM-wise. So that configuration is ARM basically putting a stake in the sand, saying if you want a dedicated laptop chip, ARM-based laptop chip that isn't Apple, that is Cortex-based, here's something that we might suggest, a 10+4 configuration, which, given the core counts of laptop CPUs these days, especially in x86, it's definitely going that way, definitely getting more cores. The question is, those platforms could arguably use access up to 15 or 28 watts, whereas right now they're still doing optimized laptop chips, maybe some semi-custom silicon, but there's a barrier that they have to push through in order to gain the performance, and this could be something along those lines. Also, these cores, as I said, scale down to edge. What happens in the data center? We'll have to wait for an ARM data center tech day for that. Actually, as I'm filming this, yesterday, the Hot Chips conference actually announced its schedule, and there's an ARM v2 and an ARM N2 for the Neoverse. They're going to be architectural talks, so that's going to be really interesting. We'll have to see what comes out of it. When are we going to get systems with these cores in? End of the year, fully expect Qualcomm to have their Qualcomm Tech Day, MediaTek to have their MediaTek Tech Day, where they're going to essentially brief or announce their next generation 2024 smartphone chips, which should be either X4, A720, and A520 based, especially if they're going to be 64-bit only. There's obviously the little Nuvia thing that Qualcomm's got going on, which I'm really interested in seeing how that develops. Lawsuit aside, I've got a video on that. You should definitely check it out. But if you have any desire to see a deeper dive into these architectures, I may actually stick them up on my newsletter rather than as a video. My newsletter is more-more.com. That's 2 O's in the second more after Gordon Moore. And that might be where I do more of a deep dive into this architecture. But if you enjoy stuff like this, please do let me know in the comments, and I'll see you on the next one.